Hello everyone. We'll continue with the classification of elements and we'll start with periodic properties. Now, first of all, what are the periodic properties? The properties which are directly linked to the electronic configuration of the atom and show a gradation while moving down the group and along the period. So those properties which are directly linked to the electronic configuration and show gradation while moving down a group and along the period. Now, trends in the physical properties. Now, which physical properties? So in general, the physical properties of the elements are boiling point, melting point, densities, enthalpy of fusion. However, here we will focus on the properties like uh, atomic and ionic radii, ionization enthalpy, electron gain enthalpy, electronegativity, valency. So all these are directly linked to the electronic configuration of the atom. So now, first of all, atomic radii. The first property, atomic radius. So generally, we all have a picture of atom in our mind. It is spherical in shape. So by considering so, it is the distance from the center of the nucleus to the outermost shell containing outermost electron. So it is the distance from the center of the nucleus to the outermost electron. Now the exact observation of the atomic radius is not possible. Why it is not possible? Because the atoms are not well defined. So their boundaries are not well defined. In case of atoms, the boundaries are not well defined. The first reason why we are not able to get the exact atomic radius. The second is we cannot isolate a single atom. So whenever we are going to find the atomic radius, there is impact of the neighbor atoms, which always gives influence on its value, on the atomic radius value, because the neighboring atoms always give influence in the probability of finding the electron cloud of other atoms adjoining them. Now, the atomic radius is of three types on the basis of bonding in the atoms. So it is covalent radius when they have covalent bonds in them, van der Waals radius, and metallic radius. So we are not able to find the radius of an isolated atom. So that's why we are considering bonded states, or we are considering molecules. So from those we will get the radius of the atom. So the atomic radius is of three types: covalent radius, van der Waals radius, and metallic radius. The first of all, covalent radius. So in covalent bonds, there is an overlap of the electron clouds of atoms. So here is an example of hydrogen molecule. So the internuclear distance of the interatomic distance is 74 picometer, and one half from the center of one atom to the half distance is known as covalent radius. Now, in case of double and triple bond, this is not. In case of double and triple bonds, the bond length is the half of the bond length is not considered as the covalent radius. Uh, so only for the single atoms, single covalent bonds, it is considered as covalent radius. So in case of double and triple, the bond in between the atoms are not regarded as covalent bonds. So covalent radius is always less than the actual radius of atom. This is due to the overlapping of the atoms. Now next is the van der Waals radius. The van der Waals radius is the internuclear distance between the two adjacent atoms belonging to two different molecules, belonging to two different adjacent molecules. Like here, there are two adjacent molecules. This is one molecule and this is second molecule. The distance from the nucleus of this to the distance of the nucleus of other atom is the internuclear distance between the two molecules, and half of this is known as van der Waals radius. Is known as van der Waals radius. And in case of monatomic noble gases, it is taken as the one half internuclear distance between the two isolated atoms which are adjacent to each other, which are at the closest approach at that time. So these van der Waals forces, so the van der Waals forces are the weak, so the value of the van der Waals radius is large because molecules are far apart from each other. And in case of gases and liquids, van der Waals radius is not considered. So it is only considered in the solid state when the molecules, when the interactions are maximum and the internuclear distance is minimum in between the two. Next is metallic radius. So half of the distance between the centers of the two nuclei, which are bonded through metallic bonds. So metallic bonds are again weaker than the covalent bonds. So van der Waals radius is the largest, and metallic radius then comes after that, and covalent radius is the smallest one. And we'll take the covalent radius as the atomic radius. And for noble gases, it is van der Waals radius. Now, variation of this atomic radius in a period. So, in generally, it decreases when we move left to right. So, let's consider the second period: lithium, beryllium, boron, carbon, nitrogen, oxygen, chromium. Their atomic number 3, 4, 5, 6, 7, and 9. So same is the number of protons, and hence the nuclear charge is considered as same: 3, 4, 5, 6, 7, 8, 9. Valence shell is 2s1, 2s2, 2s2, 2p1, and 2s2, 2p5 for the fluorine. Now have a look on atomic radii. It starts from 152 and gradually decreases up to 72 in case of fluorine. We're not considering the case of neon here uh, because neon is a noble gas, and in that case we'll use van der Waals radius, and van der Waals radius cannot be compared with the covalent radius. Here in all these cases we have covalent radius. So on moving left to right, there is an increase in the nuclear charge, which results into the decrease in size because the filling of electron is in the same shell in all the elements in a period, but the nuclear charge is increasing when we move from one atom to another. So this is the reason of decrease in size, because the effective nuclear charge increases gradually when we move from left to right. And the noble gas is not compared with the other elements of the period, because in case of noble gas we are considering van der Waals radius, and in all other cases we are using covalent radius. So obviously the van der Waals radius value is quite high as compared to the covalent radius. Next is variation of atomic radius in a group. So in a group, so we'll consider the group 1: lithium, sodium, potassium, radium and cesium. So nuclear charge is increasing: 3, 4, 19, 37, 55 atomic number, number of protons. And here the valence shell configuration shows the increase in the principal energy shell, which shows that the size of the atom is increases, and hence the atomic radius increases down the group, which is shown here: 123, 157, 202, 216, 235. There is an increase in the nuclear charge, but that is overcome by the increase of shell. So that's why here the increase in nuclear charge shows the increase in covalent radius. But as in case of a period, in case along a period, the valence, the outermost shell is same for all the elements. So hence the filling of electron is at the same distance. So the increased nuclear charge gives the increase in effective nuclear charge, whereas in case down the group, the increase in the nuclear charge is overcome by the increase in the principal quantum number by moving down the group. Now next is ionic radius. So ions are formed by either loss of one or more electron or by gaining of one or more electron. In case of loss, it is positive ion. In case of gain, negative ions are formed. So the ionic radius is defined as the effective distance from the center of the nucleus of the ion up to which it exerts its influence. So internuclear distance between the two ions, and radius of cation and radius of anion. So cation is smaller here and anion is larger as compared to the cation is shown here, because the cations are always smaller than the present parent ion. parent atom, because the loss of electron increases the nuclear charge, and hence the size decreases. So lithium 123 picometer, lithium ion 60, potassium 202, potassium ion 133. So it is always small, and more the charge, so less is the radius. So aluminium plus 3, then 50, only 50 picometer. So radius of an anion is always larger than the parent. Same is the reason, because effective nuclear charge decreases because the extra electron is there. So fluorine 72 picometer, fluoride 136, iodine 133, iodide 219. Right. Next topic is isoelectronic species, ions or atoms. So the isoelectronic species are those which contain same number of electrons but different magnitude of nuclear charge. Note, different magnitude of nuclear charge. So the ions which are isoelectrons with more nuclear charge has smaller size as compared to the other. So N3 negative is 171. Atomic number 7. O2 negative 8. Number of electron 10 in all the cases. In all the cases, number of electrons are 10. And N3 negative size is 171, and Al3 positive, it is 50 picometer only. So more the nuclear charge, smaller is the size of the atom. So that's